Hello and welcome to Toddcast 6. This is kind of a transitionary video in the sense that it's kind of going to summarize previous Toddcasts and set us up to move into the next consideration. And that is instead of or I should say instead of intra molecular features, what's going on within the molecule, we're going to move on to what happens between molecules. But before we do that, I want to make sure we get this down pat and summarized. So we will consider just hybridization bond angle, just the sort of finalize everything that we really should know. But now specifically for organic compounds, although it's what we've been doing, but hopefully it'll make sense what I mean by that. So structure summary, the things you absolutely have to know. You have to know carbon-based, nitrogen-based, oxygen-based geometry and how they mix together. So hybridizations can be sp3, sp2, and sp for carbon. It can be sp3, sp2, and sp for nitrogen. It can be sp3, sp2 for oxygen, as we'll learn over the course of this first semester organic chemistry. But want to just look at each of these structures, get the foundations down, and just keep in mind when the structures start getting more and more complex, bigger molecules, larger number of carbons, all the things that start to kick in, it's nothing more than these same features for each individual carbon, and then you consider it all collectively in the whole for the big picture of what the structure is. But for these simple molecules, this is known as methane. It is one carbon meth. It is an alkane because everything is a sigma bond. So it's all sigma bonds. So what we have is we have 4 atoms attached, no lone pairs. So again, that means a steric number of 4. 1, 2, 3, 4 things attached. Ammonia over here has 3 hydrogens, so 3 things attached and 1 lone pair. But again, that would mean 1, 2, 3, 4 electron pairs. 3 are bonding, 1 is non-bonding or lone pair. So again, 4, so that's a steric number is 4. And then last but not least, we'll consider water, which has 2 lone pairs and 2 bonded atoms in sigma bonds. So 2 plus 2, 4. So this also is a steric number of 4. When the steric number is 4, the sum of the bonds and lone pairs is 4, 4, and 4. That means I need 4 atomic orbitals to mix together to make a hybrid. So I need an S, a P, a P, and a P, meaning I need sp3 hybridization for every one of these structures. Okay, I'm going to go ahead and get rid of that drawing. And say, once you have sp3 hybridization, that should tell you immediately that the geometry, the electronic geometry, the distribution of all the electrons from the central atoms is going to be in a tetrahedral geometry. So tetrahedral is the best way to spread out that electron density so that they are as far apart as they can be in 3-dimensional space. So with that, hopefully recall 109.5 is your predicted angle, and bond length will depend on the atom sizes. Okay, geometry and shape are a little bit different. So geometry takes into account all the electron pairs, electron geometry, whereas shape takes into account just the nuclei, just the atoms. So these atoms, here's central carbon, they are also in a tetrahedral, so tetrahedral structure, as opposed to here, if I draw this here, let me go ahead and actually make lines. This would be a neat little pyramid that has a triangular base, hence the term, trigonal pyramidal structure. And then water is just bent. It's not linear. Again, 109.5. That angle might be a little bit large, but it's supposed to be 109.5, so it's a bent structure. That's your summary of sp3. So note the angles here are all 109.5, and all the bond lengths, because they're all carbon hydrogen, they're all equal. So everything for this, because of symmetry, all the bond lengths and bond angles are equal. They're all equal to 1.10 angstroms, from distance from center of carbon to center of H. And then the angle from H to C to H, no matter which HCH you look at, 109.5. Okay, the ammonia structure, because of VSEPR, valent shell electron pair repulsion, these lone pairs are going to repel these other bonding pairs down a little bit. Again, lone pairs are more concentrated, so they have a higher repulsion factor. causes the angle to be slightly lower. So instead of the 109.5 we predicted, it's 107.3. Because N is a smaller atom than H, the two nuclei have to get closer together to share. Hence, the bond length is only 1.00 angstroms. And then follow the same trend with water. You have two lone pairs, so it's going to repel even more. That angle is going to get even smaller. So it ends up, it is even less than 107.3. It's 104.5. And the bond length is 0.96 because oxygen is smaller than N. A lot of information here, but it needs to become a reflex. This has to be information that you had from general chemistry carrying over, and then it's at the tip of your tongue. You have to know the bond angles, the impact of repulsion, and the relative bond lengths, not the exact numbers. Okay. In addition to alkanes, we want to make sure we understand alkenes. That's where carbon-carbon double bond exists, and then eventually alkynes. But for alkenes and alkynes, double bond and triple bond, let's consider the alkene first. There are 3 atoms attached to this carbon, 3 atoms attached to this carbon, no lone pairs. So a steric number of 3 means I would have SPP, or if you want to say I have SPPP available, each carbon makes a sigma bond, sigma, double bond is sigma and pi. Because of the pi, I pi that out. I'm left with sp2 hybridization. Okay, so pi bonds again require p orbitals to line up side by side. sp3 or sp2 hybridization would mean trigonal planar. So trigonal planar geometry is respect to this carbon and this carbon, which means overall all 6 atoms are planar. This becomes essential and important when we start analyzing alkene reactivity. They're planar so that they can be more easily attacked from top and bottom. Okay, kind of a cool picture, but it sums up everything we have going on here. So the 109 or 1.09 angstroms, it was 1.10 for carbon-carbon or carbon-hydrogen bond when it was sp3. Keep in mind sp2 is just a little bit shorter, so the bond length is going to be a little bit shorter. Carbon-carbon bond length in alkene is about 1.42 angstroms. Here it's about 1.34. The angles, we expect them to be 120, 120, 120, but it ends up 121.2, 121.2, and about 170 or 117.6. It says 5, which means we have some rounding going on here. But the angle here should be the angle here. This interior angle should be the same for all 4. This is this bond length, 1.09 angstroms for any carbon-hydrogen bond. And then for the alkyne, and let me go ahead and give the name of these structures. This is ethene, and it is an alkene. This is ethyne, and it is known as an alkyne. Enes have double bonds, ynes have triple bonds, anes have only single bonds everywhere. Two atoms attached, no lone pair, steric number of 2. So again, let's go through our routine. SP for 2, if I count SP, I would count up to 2, or I consider SPP. My options, I have this carbon making a sigma bond, sigma, pi, and pi. So 2 pi bonds means all that's left to form a hybrid is SP, so it's SP hybridization. Get rid of all of this. Here we go. So SP, if you recall, SP has a linear electronic geometry. The angle is 180. So linear structure overall, which means all the nuclei are in a straight line. This is a sphere, if you will. They're all straight connected. Bond angle 180, there's no lone pair repulsion to push anything out. There's no bond angle repulsion. So it ends up then that this is 180, 180, 180, 180. Carbon-hydrogen bond is 1.08, which follows the trend. 1.10 for sp3, 1.09 for sp2, 1.08. And then 1.42 was the alkane version, 1.34 for the alkene, 1.21, which means it gets substantially shorter. The carbon-carbon bond gets notably shorter when it involves sp hybridization compared to sp2 or sp3. So just remember, more S character, more S features. Bonds are shorter, stronger, and compound is more acidic. Okay, that's our summary. We have to know these functions And we're going to start piecing together molecules, and you have to be able to go back to the fundamental geometry of each atom and then combine it into the big picture, what the overall geometry of the molecule is. Okay, basics of structure. So molecules will get more complicated. So we've yet to cover what this means when I draw just this sort of structure. So just to give you a welcome to the party heads up, every point that isn't labeled represents a carbon. This point here, if it's not a carbon, we have to specify. There's an O. Had it been a nitrogen, I would have put an N. But all these points are unspecified carbons. And then anything attached, we point out the O's and the N's, the non-carbon. There is also the feature of keeping track of the hydrogens on here. So this carbon has bond O, bond to carbon, and a double bond here to carbon. So 1, 2, 3, 4 bonds, it's set. This carbon has 1, 2 bonds to this carbon, 1 bond to that carbon there. So it's missing a bond. And so we assume whatever is missing is in carbon-hydrogen bond. This carbon 1, 2, 3, and 4 to the O, so it's good. This carbon right here, 1, 2, 3, so it's missing one. So I need to put in the H. The fused carbons, 1, 2, 3, 4, good, good. This one, 1, 2, 3, 4, that's good. This one here, 1, 2, so it's actually missing 2 hydrogens. One will be coming out, one will be going back. This carbon here has a bond to O, a carbon to carbon, so it is missing an H. So if the OH is in front, the H is in back. This carbon here has 1 to O, 1 to carbon, 1 here, so it's missing a fourth, so it has an H. Oh, that was terrible, sorry for my horrible drawing. I'm going to just cut to the chase. There's an H here, an H here, and an H here. So that covers everything, my carbons and my hydrogens, but you are expected to recognize that we are not going to show these connectivities. We're just going to assume you can recognize that those are carbons, and if it doesn't have 4 bonds, that you fill in the rest with H's. Okay, this is a compound known as catechin. It has lots of double bonds, and something you're going to learn is that when you have lots of color bonds or lots of double bonds, and they alternate, double, single, double, single, double, single, single here, and same thing here. When you have that, and you have atoms that are non-carbon, so-called heteroatoms, oxygen, nitrogen, sulfurs, when you have those combined, you typically have a compound that is colored in nature. So catechins typically are found in colored vegetables, if you will, they're found in lots of things, but I'm going to consider vegetables for now. Leafy green vegetables are rich in catechins. And catechins are just really good because when you have lots of carbons, double bonds, you can actually start reacting more readily. So this is an antioxidant. We'll go into a little more detail other than oxidation is reaction with O2, which has, as mentioned, these highly reactive single electrons known as free radicals. It has 2 radicals, so it is called a biradical. It reacts with everything, which is why when we eat food, it reacts and breaks it down because it's so highly reactive. But because it reacts with us, we run the risk of having, oxidative damage to our bodies. So we must consume antioxidants that can reverse the oxidation process. So when our body is damaged, it can work backwards. Catechins are really common in good foods that will have antioxidant-rich behavior. So this is just a well-known antioxidant. Okay, that aside, we'll ignore the bio aspect and get into the chem aspect. So which carbons are sp2 and which carbons are sp3 hybridized? This should become kind of a reflex that you remember that to form a pi bond, it has to use a p orbital. So I'm going to draw p orbitals for everything that has a pi bond. So if you use a p orbital, again, you have available to you sp and p, but for sp2 of your pi bonds. For the ones without pi bonds, ones who required us to draw two H's or to have two things coming off, there are no pi bonds, so the SPPP, those be sp3 hybridized. So recognizing in structure sp2s, sp2s, and sp3s. So hopefully this is pretty straightforward in how we're going to apply our structure knowledge. So this is summary-wise a good point to say, okay, we're solid on this, time to move on to a different topic next time. So we are all done. So thank you for playing along, and I will see you at the next podcast. Bye.